Okay, getting back up, problem number 14. We have a derivative. We find that f of root e is 5, and we're asked to find f of e. Well, once again, this is the fundamental theorem of calculus. Part 1, we know if we integrate from a to b of f prime of x dx, we get f of b minus f of a, but let me chuck the f of a over here, like that, same as we did on a previous problem. So in this case, we are asked to find f of e, so that's going to be that one. We know f of root e, that's going to be this one. And so if we just sort of set this up, f of root e would be the plus the integral from root e to e of f prime of x dx. That will be f of e. Okay, so and again, if you just look at this very carefully and note how it matches up with our fundamental theorem using a's and b's instead of e and square root of e, you see it matches up exactly the same. So once we've done the sort of the setup here, we can just go ahead and plug in what we know. And that should give us our answer. F of root e is given as 5. We're integrating from root e to e. F prime happens to be 2 over x dx, and that will give us f of e. Okay, so how do we integrate this? What we could probably do, root e to e. We'll take the 2 out, and so now we're just integrating 1 over x dx, which is obviously the natural log. So the integral of 1 over x dx is the natural log of x. We don't need absolute values here simply because the root e is going to be greater than 0, and so is e greater than 0. Now we'll go ahead and substitute those guys in. So our fundamental theorem says that we're going to substitute in the upper bound first. This is the natural log of e. We substitute in the lower bound, which is the natural log of the square root of e. And if we can clean that up, we'll have our answer. So you should know the natural log of e is 1. And this is going to be 1/2. You just might want to note the log of root e is the same as the log of e to the 1/2, when the 1/2 can come out front. And the log of e is 1, so that's just 1/2. So our inner parentheses here, 1 minus 1/2. It looks like we have 5 plus 2 times 1/2 is f of e, so that's 6. Okay, so not terribly bad. We're looking for 6 as the answer. There it is, D. Number 15. This looks like a straightforward integration problem. Unfortunately, there is no easy way to do u to the n du. Right? We could say u is x cubed plus 1, but then du would require 3x squared dx, and we certainly don't have that. All we have is 1x squared. We cannot introduce variable quantities. So this is sort of out on its face. If we look at some of the choices, we might suspect that we have to do some algebra. Sure enough, this is going to be the right answer. We have to expand the x cubed plus 1. So x to the 6th plus 2x cubed plus 1. We know how to expand a binomial pretty easily and then integrate term by term. So x to the 7th over 7 to x to the 4th over 4 plus x plus c is the answer. There it is. A little bit of algebra before the calculus. Number 16. A function increases when its derivative is positive. And again, I just sort of put this in there to remind you what increasing, decreasing is related to positive derivatives. That was not given on the released exam. This was the problem here. The derivative is this positive quantity. We might want to note here that f prime is positive. F prime is defined for all x values, right? The absolute value is certainly defined for all x values. And we might also want to note that f prime is 0 when x is equal to 2. And you can just sort of look at this and go, yeah, this derivative problem says that we have positive all the time. It's always defined. This f prime is always defined, except when x is 2, f prime is still defined, but then f prime would be 0. Okay, so what we're looking for is a function that's always increasing, except at 2, where the function would not be increasing. So that doesn't always increase. Neither does that. Neither does that. This one's sort of interesting. It's increasing and then increasing. This, in fact, is the answer down here. Increasing always, and has a 0 slope tangent at 2. Why not this one? Here, if this were the original function, if it were, then you could not talk about the derivative at the point of discontinuity. Here, f prime of 2 would be undefined in this graph. But we know that f prime of 2 is in fact equal to 0, right? We know that because we were given the derivative. You put 2 into here, and sure enough, you would get 0. So the choice D is out. The choice E is the right answer. Number 17. A function decreases when its derivative is negative. Well, again, I threw that in there just to help remind you how to do that. That would not have been given on the AP test. Here's the graph of a derivative. Which of the following intervals is f going down? Okay, so one way of thinking about this is everything above this line is positive. Everything below this line is negative, right? And we're looking for where the function is decreasing, so we need negative values. Those are negative values, and those are negative values. Notice that between 2 and 4, the derivative is positive, right? It's up here in positive world. And again, this is a graph of the derivative. This is the derivative, right? They told us that. So all we're doing is we're looking for numbers between 0 and 2 and between 4 and 6. So 0, 2, 4 to 6, that's the answer. Number 18. Here's a function, f. We're given the derivative, f prime. What's the approximation for f 1.2 using the tangent line to the graph? Okay, so here's the prompt. Y minus y1 m times x minus x1. We know that x is equal to 1. We know that y of 1 is 4. So we need to get this derivative. What is this derivative here? The derivative, well, we were given the derivative. The derivative is this. We need to evaluate that at 1. So f prime of 1 is 4 minus 1, which is 3. Okay, so cleaning this up a little bit, we have 4 plus 3 times x minus 1. This is the equation of the tangent line. Now, the key on linear approximations, right, linear approximations, is that the function, the curvy function, whatever it looks like, is about the same as the line. So we don't know what f is. It's not given. I suppose we could, you know, if we wanted to, we could integrate f prime, integrating 4 minus x, and get 4x minus x squared over 2 plus some constant. We could play with that and actually come up with the function, but we don't need that. what we're trying to do is to use this tangent line as an approximation for 1.2. So f of 1.2 is about L of 1.2, and L of 1.2, right? We know what L is. This is L. This is our line. And so L of 1.2 is 4 plus 3 times 1.2, take away 1. 3 times 0.2, which is 0.6. So 4.6 is the answer. I think if you actually chase down and actually find the original function and then calculate C, you actually get this answer here. But that's not what they're asking for. They're not asking what is f of 1.2. They're asking what is the approximation using the tangent line. Number 19. Slope of the tangent line to the graph. Well, again, just a straightforward derivative problem. Y prime, we have, what do we have? We have bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. This is quotient rule, right? So cleaning that up, we got x plus 1, take away x, add 1 over x plus 1 squared, which is 2 over x plus 1 squared. And then we're supposed to evaluate that when x is equal to 1. So 2 over 2 squared is 4, which is 1/2. There's our answer, 1/2. Oh, I can't get that answer. So am I right or am I wrong? Where did I go wrong here? Okay, bottom derivative of the top minus top, aha, silly me, minus top, which is x minus 2 times the derivative of the bottom, all over the bottom squared. So this would be minus x plus 2, so this is 3, so this is 3/4. Sorry about that misread. Choice D. You'll make mistakes. You know, if the answer's not there, go back and check your work. The function f, whose graph consists of 2 line segments, is shown above. Which of the following is true for f on the open interval from A to B? The domain of the derivative is from A to B. Well, that's not true. That's false, because we know that you cannot find a derivative, no derivative, at a corner. You cannot talk about the slope of the tangent line there, so that's false. F is continuous from A to B. Well, that's certainly true. I can draw my picture without picking up my pen, so that's true. And the derivative is positive on the open interval A to C. Well, A to C is just right here, and sure enough, the function is increasing, so that's also true. So it looks like we have 2 and 3 only. Choice D is the answer. Number 21, find the derivative. It's just a straightforward derivative problem. You should remember the derivative of secant is secant tan. So we bring the 5 out, we have the secant of 3x times the tangent of 3x, and then use the chain rule times 3. So 15 secant of 3x tangent of 3x. Quick problem. 22. We've got here, we're trying to evaluate this definite integral, right? And we know that f, this f right here, that's in here, is the derivative of g, and we know what g is. So let me just write down the derivative of g. The derivative of g is 2x minus 3, right? So we just sort of have to, you know, play with this a little bit. We have the integral from 1 to 3 of f, but f is the derivative of g, and we know what g is, so here's f. It's 2x minus 3. So that's all we have to do. We'll find an antiderivative, which is x squared minus 3x. Now, we could put plus 4 here. That would be okay. We could put plus 40. We could put 407 pi. It doesn't matter. Remember, this constant, whatever that constant is going to drop out when we evaluate between 1 and 3. That's why we don't put the constant in on definite integral problems. But I'll just go ahead and throw it there. So we have, we're going to put the upper bound in. We'll put the lower bound in. We put 3 in, so we get 9 minus 9 plus this constant. Then we put the lower bound in, we get 1 minus 3 plus this constant. And sure enough, the constants go away. So whether you put 4 in there or 407 pi, it doesn't matter. What do we get? We get 0 here, or actually we get C. And then we're taking away 1 plus 3 minus C. So the C's go out, and negative 1 plus 3 is 2 is the answer. Okay, choice C. 23. The graph of an even function consists of 4 line segments as shown above. Even means, remember what even means, that f of negative x is the same as f of x, right? Symmetric about the y-axis, and we sort of see that here. As x goes to 0, what is f of x minus f of 0? Well, it looks like, first of all, we'll note that f of 0 is 0. So as x goes to 0, we actually just substitute in here, and we get the limit. Well, we're going to substitute x is equal to 0. So we get f of 0 minus f of 0. And is that equal to 0? That's our question mark. Well, f of 0 is 0. 0 minus 0 is 0. That's true. So that's a true statement. We're trying to find one that's false. So no problem with A. Part B, x goes to 0. Well, here we could not do direct substitution, because if we do direct substitution, we would get f of 0 minus f of 0 over 0, which would be 0 minus 0 over 0, which is 0 over 0, which is not the answer. So we can try L'Hopital. That's always a legit approach. So this is the limit as x goes to 0. The derivative of the top is f prime, and the derivative of the bottom is 1. Now, what happens to the derivative as x goes to 0? Well, that's an interesting question, right? So we're supposed to be putting 0 in here. Well, if we approach 0 from the right, we notice the slope here is always 1. But if we approach 0 from the left, the slope here is minus 1. So in fact, this is going to be undefined at x is equal to 0. We know we cannot find derivatives at a corner or a cusp. So this is false. Just as a purpose of discussion, let's look at the other choices. What happens when x goes to 0? We have f of x and f of minus x. Well, from our definition of even functions, we know that f of minus x is in fact f of x, right? That's one of the things we set up here. So I could rewrite this and write this as limit as x goes to 0, f of x minus f of x all over 2x, and that's the limit as x goes to 0 of 0 over 2x. Well, 0 over 2x is always 0. So that is true. No problem there. This one, if we're trying to figure out what's going on, let's see, if we do direct substitution, we get f of 2 minus f of 2 over 2 minus 2, which is 0 over 0, which we can't make any sense of. So we'll use L'Hopital on this one. And we got limit as x goes to 2. The derivative of the top is f prime. The derivative of f of 2 is 0, right? That's a constant. And that's 1. So all we have to do is now we just substitute in. And so f prime of 2. What is the slope at 2? So we look at the graph. the slope at 2, here's 2, and the slope right here is in fact 1, right? So that becomes 1 over 1, which is 1, so that's true. And at 3, sort of a similar discussion, we would get f prime over 1, and then take the limit as x goes to 3. So that's going to be f prime of 3 over 1. And so what's the slope at 3? Well, again, we see a corner there, so that does not exist. This is undefined. Right? So it does not exist. That's actually true. The only one that's false is choice B. Tricky problem. 24. Parametric functions. We studied parametric functions in pre-calculus. You might recall that this is in fact an ellipse. Let's get a little sketch going. If I take and divide the first equation by 5, I get this. And if I divide the second equation by 3, I get this. Probably remember doing this at one point. Then we square both sides. Squared over 25 is cosine squared, and y squared over 9 is sine squared. And then we add these up. So we get x squared over 25 plus y squared over 9, cosine squared plus sine squared. Recalling our basic trig identity, this is equal to 1. So we have x squared over 25, y squared over 9 is 1. Our major axis is 10 units long, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Our minor axis, 1, 2, 3, 3. Here's our ellipse. It looks like that. Okay. Let's look at the discussion of what's going on. dy dx is undefined. We could certainly, what happens when t is 0? Let's figure out where t is equal to 0. We can play with that a little bit. T is equal to 0. T is equal to 0. Remember, the original equation was given. X is 5 times cosine of t. So at t is equal to 0, x is 5 times the cosine of 0, which is 1, right? 5 times 1 is 5. And at t is equal to 0, y is 3 times the sine of 0, which is 3 times 0, which is 0. So we're at the ordered pair 5, 0, which means we're all the way over here on the right side of our ellipse. Okay, so at that location, what can we say about the derivative? Well, it's pretty obvious, I think, just by looking at it, that the tangent line is vertical, which means dy dx is going to be undefined. So dy dx is undefined. Slope of the tangent line, rise over run, undefined. Certainly doesn't, this says something about change of y with respect to t. We could find that just using calculus if we wanted to. And we've got y is 3 sine t, so dy dt is 3 cosine of t evaluated when t is equal to 0. I should read the problem. Which of the following is false? I was going to say this gives us equal to 3, right? The cosine. So this is true. This is true. This is true. Dy dt is undefined. No, that's false. In fact, we found what dy dt is. Dy dt is equal to 3. Let's check the other ones out. Dx dt, x is 5 cosine of t. Dx dt is negative 5 sine of t. We're going to evaluate that at t is equal to 0. And that gives us 0. So that's true. And the last one, the graph of f has a vertical tangent line, and we saw that just by graphing it from pre-calculus. Yeah, so the one that's false is C. That is the correct answer to this problem. Okay, 25. Good. We got this implicit differentiation problem. Doesn't look terribly impossible. So we'll differentiate implicitly. Okay, so the derivative of the product is the derivative of the first times the second plus the first times the derivative of the second. I like to do dy dx. That takes care of that. The derivative of minus 3x is minus 3. The derivative of y cubed is 3y squared dy dx. Remember, we're using implicit differentiation here. And the derivative of 3 is just 0, so I don't have to write it, 0. So we've done the calculus. Now let's go ahead and solve for dy dx. And so using linear equation techniques, dy dx, hopefully you can do this in your head by now. We're going to move the 3 across, and we'll move the 2xy across, and then we're going to divide out by the factored form. So we have x squared. This would have been brought over here, minus 3y squared. Okay, so there's the derivative. And then we're asked to evaluate this at the point -1, 2. As long as we can keep track of our signs, let's see, we have 3 minus 2 times x is -1, and y is 2. And then on the bottom, we have x squared, which is -1 squared, minus 3 times y, which is 2 squared. We'll just clean that up. What do we've got? We've got 3 plus 4. So that's 7 on top. On the bottom, we've got 1 minus 3 times 4 is 12, which is minus 11. So we're looking for minus 7/11. Minus 7/11, choice A. Implicit differentiation. Number 26. Function is given here. What's the derivative? This is fundamental theorem part 2. Hi guys. This is an integral function, and to find the derivative, we simply take the 2x and pluck it right where the t is. So we get square root of 2x quantity squared minus 2x. The interesting part here, we do have to use the chain rule. So follow this by the derivative of 2x, which is 2. So cleaning that up a little bit, we have square root of 4x squared minus 2x with the 2 in front. Last thing we have to do is evaluate this when x is 2. So f prime of 2 is 2 times the square root of 4 times 4 minus 4, which is 2 square roots of 12. Is that a choice, or did they clean up the radical? 2 square roots of 12. There we are. I suppose that we could have seen if we clean up radical, that would be 4 square roots of 3. I mean, be able to do that if you have to, but we didn't have to do it in this problem. Okay, number 27. We have this definite integral from 0 to 3 of f. That's equal to 6. And we have the definite integral of f from 3 to 5. That's 4. Note, by the by, if I just look at these together, and just ignoring the f for a minute because they're the same, the integral from 0 to 3 plus the integral from 3 to 5 is the same as the integral from 0 to 5. And in this case, it's given to be, this is 6, and this is 4, so this would be 10. So the integral from 0 to 5, let's just write that down. The integral from 0 to 5 of f of x dx happens. Okay, let's look at the problem at hand. We've got the integral of a sum, so let's break that up into 2 integrals. Integrate from 0 to 5 of 3 dx plus the integral of 2 f of x dx, and that's also from 0 to 5. Okay, we can move this constant out. Oops. Can I try that again, Joe? 2 f of x dx. Okay, we can move the constant out front, right? And then we know what this is. This we've already reasoned out that that's equal to 10. So it looks like the answer to our problem is going to be this integral from 0 to 5 of 3 dx, that's just 15, plus 2 times 10, plus 20. So 35 is the answer. Choice D. And by the by, and just as an aside, when I see that, I think graphically this says I have a constant function of 3. Here's y is equal to 3, and I'm going between 0 and 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I'm just finding this area in here, and obviously 3 by 5 is 15. Okay. 28. Sine inverse. Well, this is one that I guess you just have to know. The derivative of sine inverse of u is 1 over the square root of 1 minus u squared. And then don't forget the chain rule, du dx. So u in this case is 5x. So we have 1 over the square root of 1 minus 5x quantity squared, and then times 5. So choice E. Okay, that's it. We'll do the calculator problems in a separate video.